Hello again. It's me again, Rommel. We continue our lecture, and now we stopped in the convergence result in establishing the convergence of the Landweber iteration. So let me just browse it over here. Apologies for all the changes in the slides. Here we go. Note that in the chat box, I once again posted the link to the slide, to the updated lecture slides. I added more stuff on it. Okay. And then I think we stopped. Okay, so just a little review. We ended with this theorem, which establishes the convergence of the Landweber iteration for linear problems with the stopping criterion determined under the discrepancy principle. And then, so now we are ready to derive the convergence rates under the following source conditions, which, if you look at it, it's something like the one we used for Tikhonov regularization, but this time we let this parameter here, nu, is somewhere there. Note we let nu to be just let nu to be a finite number, and still omega is in the orthogonal complement of the null space of A. Note this. This is an abstract smoothest condition because we usually associate the operator A as a smoothing operator, and then there's so much results that we can already use here to establish this one. In fact, from lemma 3.19, we derived this estimate of the approximation error on the left-hand side. Okay, which is less than equal to C1 times n delta to 1/2 plus this one here, somewhere there, okay, that one. And then, so now what we need to do is to provide an upper bound for n delta. I think it works if I put it there. Yeah, it works there. So now we just need to derive an upper bound for n delta. Okay, and for this one, we can work on this a bit later on. So now let's derive an upper bound on the exact residual a sub x sub n minus y. So let's use this. Let's do some proof for this helpful lemma, which gives us a bound for the residual at the nth iteration where we have an exact data, okay? And then from there, we also use the source conditions here. So let's put it here, there, okay? So now to show it, let's try to outline the proof of that one and see how the source conditions apply. We should raise it a bit. Okay, so it's like this. First, we start from the definition of xn in the exact case. So it's like this. I think my eraser is there. That's fine. So, for instance, if I have something, if you recall from the definition of x sub n, it's easy to derive by applying the operator A. So that a sub x sub n minus y equals this one, minus y minus a times a star times x sub n minus 1 minus y. Okay? And then from this one, we manipulate it a little. And I think I missed something here. That should be A star times, oh, A times A star. I'm missing a term there. That's A there, okay? And then by grouping these terms accordingly, okay? Okay, so that means we can treat this expression as in terms of some operator I minus A times A star times AXN minus 1 minus Y. Notice this is just identity. Just imagine there's an identity there if you get confused, you know. Okay, and then note that x sub 0 is 0, as we can see, and then let's use some induction hypothesis, and it's easy to see that by induction, it's easy to derive that A sub x n minus y is equal to this one, A star raised to n, actually there's a minus there, times y, okay? It's easy to derive if you start at n equals 0, then notice that this term here will disappear. That's why you have minus y here, and then just use an induction there. And now by applying the fact that y is equal to ax, as you can see here, if you apply the definition of y, it's equal to a times x daggers, it's like this. And then by spectral calculus, we can move this a here over here, so we'll have something like this, a times I minus, because we moved a here, we must shift, that should be n, we must shift the order of the transpose here. So we have A star A. And then by applying the source condition on x dagger, we further get this one. Nu times omega. Okay? And then from that one, we can further deal with this one by taking the norms. In fact, if you take the norms of this one, I can just put it up, maybe just write it here. Was the norm of A times I minus A star A. And in fact, we can just apply property of norms so that this is less than equal, so that we can express this as a product with the norm of omega. And now, by looking at this one over here, from spectral calculus, we can imagine that this is equal to some as a function of self-adjoint operator. So in fact, if we have something like f of t equal to 1 minus, it's actually over there, then 1 minus, and I forgot something actually, that should be eta there. Eta, and then minus eta over there, so just take notes. Okay. Over there, and then that's 1 minus eta times t raised to n times t raised to eta. Okay, and then from spectral calculus, yeah, I think that's, I mean that's quite doable there. So, and also by taking the norm in terms of f, then this will be less than equal to the supremum of this equation expression here. Let me just check on something. Okay, I don't really need to. I don't really need to move the operator here. Let me just rewrite it. Okay, so here I can just try to I move this one, but it's still the same. It's also from spectral calculus. Note we can write this one as in this way: A times A star raised to n times something like that, and then times A. So this is like of the form of f of A times A star times A. Okay. Okay. And then from this one, from spectral calculus, this will be less than equal to that one over there, that supremum of the following, that's square root of t. I'll just use square root this time, times the absolute value of f of t. Okay, so that's the absolute value of 1 minus eta times t raised to n times t raised to nu, where we take the supremum on from 0 to the norm of A square. Okay, and now we need to handle that this supremum over here, and here's how to deal with it. And let me just check out this one. Okay, and to help us understand this one, we can let S be equal to eta times t, as we have as suggested there. And note that our step size, eta, is bounded between 0 and norm of A raised to minus 2, and t is from 0 to norm of A square, and that means that eta times t is bounded above by 1, right? And then by doing this variable substitution here, we can get the next expression there. So this will be equal to the supremum of, so I'll leave the details on you guys. So that's 1 minus s raised to n times s to the eta nu plus 1/2. Okay, and then times eta to the minus v, minus nu minus 1/2, and then times. And this time we take s from 0 to 1. Okay, and note that if you look at this resulting function here, we can just simply focus on taking the supremum on this part over here, because this one has nothing to do with s. So again, by calculus, okay, now if you take this function here as phi of s, and it's easy to see by calculus, if I can you can apply some derivatives there, that you can achieve the maximum on 0, 1 at s star, which is given on that one. Okay, so just use calculus there, use differentiation. Just use the fact that phi prime of s star must be 0, and solve for that equation there, and then you'll get that one. Okay, and then by plugging in s star on this value over here, so this will be less than equal to use s equals s star, and that will be equal to this value over here. So that's we just write it, mu plus 1/2 over n plus mu plus 1/2 raised to mu plus 1/2 times also something about oh yeah, I also forgot that there's actually some eta yeah, some eta over there. Okay. Then yeah, we can just also put it there. Okay, now if you look at this factor here, let's see how we can get the bound that we actually need. So here are details on that one. If you let mu, let's say you have eta plus 1/2, then notice this bound over here. Let's call it, how do I say that? M sub nu, or M sub mu for that value here. So you have M sub mu be equal to, that's mu over n plus mu. Okay. And then what we can actually get here is that we have this important result from also Engel's book. So this is like n mu plus n sub raised to mu, and it's easy to see. Well, actually not that easy to see. But if you try to write this one as mu raised to mu times n plus mu raised to minus mu, then there are two scenarios that you have to consider here. For instance, if let's say mu is less than 1, okay? If mu is less than 1, then if you notice this term grows larger than this one. In fact, this will be bounded by 1. Okay? And then, in fact, we can bound this term further by letting mu be equal to 1. So this will be bounded above by n plus 1 minus mu. Because if you have n plus 1 over here, then we'll have some. And that's also from the fact that 1 over n plus mu is 1 greater than 1 over, is it? Yeah. It's greater than 1 over n plus 1. Okay? And on the other hand, if mu is greater than 1, then it's easy to see that we'll have the same bound over here. So you need to have mu raised to mu over here times n plus 1 raised to minus mu. Okay? So these are the two estimates that you will consider. But note that for mu is greater than 1, notice that this one has an effect in the growth of this expression here. So you can, so mu, in fact, mu raised to mu will be greater than, very much greater than this other factor here. And then you can also bound this one by n plus u raised to minus mu. Unlike that, if mu is less than or equal to 1, then this will just be bounded by 1. However, in our source condition, we only consider, because this one is finite, this must be finite, so we don't consider the case that mu is greater than 1, so we'll just consider this one, okay? And that's why if we bound the error further, then we will get some I forgot the. And further, we can actually bound this one by this one. Okay. So this will be this one. This will be bounded above by some constant, or not yet really, some constant raised to v. So here, we just let this one c raised to nu, which is independent of nu. So that's c raised to nu times n plus 1 raised to minus nu minus 1/2, something that is written there. Okay. Okay. So we have a bound for a sub x sub a to the residual at the exact case. Now, this is useful enough for the next step. Okay. And note that in the less than equal part over there, forgot to mention that. Actually, I forgot to mention that in this part over here, you need to bound, do a bit of take note that if you substitute S star here, then you will actually end up with 2 factors. One of those factors will be less than or equal to 1, and this is the useful bound that you will need. Okay, not really, not useful, but the bound that you must use. Okay, okay. Now by lemma 3.22, by using this one over here, what we can get further is that result that that's actually there. Okay, and then if we plug it in, and then you will actually get that result. Okay, so here you will wait, that should be here. Okay, okay, so that's there. Okay, so that's the result that we need. And now, how do we use it? It's by using the discrepancy principle. So from that previous result, if you let n equals n sub delta minus 1, where n sub delta is from the discrepancy principle, then it's easy to see that the norm of a sub x sub n sub delta minus 1 will be less than or equal to that one over there. So c times nu times n sub delta to the minus nu minus 1/2 times norm of omega. Okay, and then that's actually what I'm. Oh, that's not up. I went ahead, sorry guys. There, okay. And then because this is still before the stopping criterion n delta, so this residual here is still less than. It cannot be greater than tau delta, so it must be greater than tau minus 1 times delta. Okay, that's from the by the discrepancy principle. Okay. Okay, and then actually from and then actually by solving for n sub delta there, you can actually derive an upper bound from n sub delta. So if you solve for n sub delta, so you just simply manipulate that inequality, you can actually see that n sub delta is finite. Okay? As you can see, it's bounded above by some constant. And then consequently, we can use that for the error bound here, because note that for here, we needed an upper bound here for n delta. And by using that one, we can actually see that it's actually equal to this more useful bound, okay? And it gives us a hint that the approximation is of order optimal because of this one. If you look at this term here, this looks familiar, okay? It's also the same convergence rate from the Tikhonov regularization. And with that, we have the convergence rate for the Landweber iteration by discrepancy principle. So it's like this. We can also derive the normal x sub n delta, x dagger, its best convergence, its optimal convergence rate. Convergence rate is also like this. Okay? Note this is an optimal convergence rate. That means it's the best convergence rate that you can get. So as you can see, since we already have a bound on this first term here, we need a bound on this term. Okay, and that's what we will do. Okay, so now to derive that one, we need again start from the definition of x sub n, which is the Landweber iteration for the exact data. And then by subtracting both sides by x star, we have x sub n minus 1 minus x star minus eta times a star times a sub x n minus 1. And then we need to use the fact that y is equal to a x dagger, so we put it there. Okay. And then, similarly as in the previous one, in fact, I should use x dagger, not x dagger. Okay. And same as in the previous computation, this can be written as that one over there. That's I minus eta a star a, because note that we can actually factor out a over here. There, okay. Okay, and then from that one, we can also, same as in the previous lemma, also by induction and by source condition, we can also see that x sub n minus x dagger is equal to minus of I minus eta a star a raised to n times x dagger. And again, by the source condition, we can put, it's safe to put a star a here raised to nu times I minus eta a star a raised to n omega. Note that since you have a star a there, note that you must also have a star a here. Okay? It cannot be like a star a and then you have a times a star. If you see that one, there's something must be wrong. Okay? And then that's a useful bound because we can apply interpolation inequality to estimate the norm over there. So that will be equal to this one. Did I put norm of omega? Yeah, don't need to prove. Okay, so again by interpolation inequality, if you recall, a star a raised to r. Now let me just write it. R over Q times norm of Z to be 1 minus R over Q, where Q is greater than R, 0. Okay, now for this one, if you look at the last estimate, this is simply our, you can simply let this thing here as our Z, and then we let R be equal to nu, and Q be equal to nu plus 1/2, and then from this one, you can bound this by the following. So that's A star A raised to nu plus 1/2 times Z. So that's the entire estimate there. Raised to, note that R over Q is just 2 times nu over 2 times nu plus 1. So I'll just write it here. Times the norm of Z, so that's the other one over there. N times omega times 1 minus R over Q, that's just 1 over 2 times nu plus 1. Okay, and then by looking at the first term here, note that this one here, we can break this up in like this. A raised to mu, then times A star A nu to 1/2. And then we can just shift it a bit. It's fine because they are both the same in terms of the same operator as self-adjoint operator. Okay, and then from that one, if you look at this thing over here, okay, and now also if you look at this one, okay, it looks familiar actually because you will see that it will just be equal to a term in terms of A star A. In fact, we can use the fact that this one, is this the one that we derived earlier? Yeah, this one. If you look at this one, if you look at the norm of this one by triangle inequality, then notice if you substitute this one, this is just xn minus x dagger, right? And then by using the fact that A star A 1/2 of Z square is just equal to the norm, the square of the norm of A times Z, then we can write this one as this one. A times xn minus x dagger, and you have still a square over here. Note this one, this has a factor of 2, so you can just use it here to apply this inequality. Okay, and then also, if you look at this one, by spectral calculus, same as the function that we used last time, it's easy to see that this one is bounded above by the supremum of 1 minus eta t raised to n. Okay, times norm of omega. Okay, and then also by take, same as in the previous one, we take t from and then by applying the substitution of variables, it's easy to see that this is bounded, this supremum here is bounded by 1. So that's equal to 1 times norm of omega. So therefore, this is actually, the entire bound is bounded above by this 1 times norm of omega. Okay, so just use the fact there that if you let s again be equal to eta times t, and because s is greater than equal to 1, then this one here, 1 minus eta raised to t raised to n, can be bounded above by 1. So you have the omega there. Okay, and then, so we have that useful error bound over there. And in fact, I forgot the. Okay, and now, by using the fact about lemma, fact given to us by lemma 3.9, in fact, by just using this bound over here. So if we use a bound that we used last time, in fact, we can use the fact that this identity related to a sub x n minus y. So that's, and now it's in terms of the regularized approximates with delta. With delta here, then you have minus delta. Note they are equal, right? And then we can rewrite this one in this way. That's minus, oops, that's yeah, minus y delta plus y, because I'm taking out the minus sign here. And then we can again apply triangle inequality, and then we get something like this. Yeah, that's where I stopped over there. So what you can't do is, by applying triangle inequality for that one, so that will be like, and then by let's just apply n sub delta right away. So we can let n the norm of a sub x sub n delta minus y be less than equal to that one. Yeah, that one. And then from that one, we have some useful results from lemma 3.19, and also from the from the definition of n sub delta from the discrepancy principle. Note that this term here is less than equal to tau delta, right? Okay, and then also from this one, from lemma 3.19, we know that this is bounded by delta, so you can recall from the notes. So this is bounded above by tau plus 1 times delta. Okay? And where do we use it? I forgot to mention. Actually, forget to mention how do we. How do you use that? Because from the bound that we just arrived in terms of xn minus x dagger, you can use that one. Then you will have something like this, so that will be equal to a times, you can distribute a there, right there, minus y raised to 2 times nu over in fact, we can use this one in terms of n sub delta. And we can use this one. Okay? And then by plugging in that one, then you should be able to get the necessary bound that we need, right? So that's less than equal to this one raised to 2 times this one, then delta times 2 times nu times 2 times nu plus 1. It's just the same error estimate from the regularized solution here. So because x sub n delta and delta, note this is also bounded by some constant nu times delta to the 2 nu times 2 times nu plus 1. So the error estimate holds. Okay. So again, as I mentioned, the convergence rate is order optimal. And then, so we know that the Landau iteration under the discrepancy principle is a convergent regularization method. And to illustrate that, here are some numerical simulations by the discrepancy principle. And here we test different values of tau. And then we just take the same step size 0.1. So as you can see here, as tau gets closer to 1, of course, note that we have reconstructions that are getting better. And notice that as tau gets closer to 1, we get we need more iterations leading to better reconstructions. And that isn't so surprising after all, because our exact solution is smooth. So and if your solution is smooth, and because with the source, as guaranteed by the source conditions, then we are achieved very accurate reconstruction, because when we have a smooth solution, then we are guaranteed of an optimal an error estimate. Not in the case where we have a non-smooth solution, as you can see here. Notice that by using discrepancy principle, because our source solution is not smooth, notice that our reconstruction is very smooth. But if you look at this one, note that although it captures the non-zero, rather the non-zero parts of the solution, I mean the parts where it's piecewise constant, note that it's not as accurate as in the case where we have a smooth solution. Okay, so that is something about the linear regularization methods for linear in inverse problems. So since we actually have more time, I decided to touch on a related topic, which is something about, here's another one, I forgot. And here's also another one. If you have a solved solution, as you can see, we tried this for different noise levels. So from left to right, we have from delta 0.1 and with the same tau. Okay, And then if you notice that, of course, this illustrates the regularization property where this tells us that as delta goes to 0, the regularized solutions converge to the exact solution. So this illustrates this one. So as you can see from left to right, top to bottom. So notice that we can get better reconstructions. Of course, at the expense of using more iterations. Of course, you have to do them anyway. And then now we go to a topic which I did not really intend to touch in the first place, but I think it will benefit the course. So now let's consider nonlinear problems, but we'll just touch the Landweber iteration for nonlinear problems. So far in regularization theory, the theory for linear problems is actually more mature than in the nonlinear problems. Okay, and it's also an important thing to consider because across inverse problems, a lot of problems involve solving the parameter of which is related to a PDE, like for instance in diffusion models where given some measurements related to the solution of a differential equation, you want to find the parameters that lead to that to that solution, okay, or the set of observations given by a PDE. Okay, and I mean those sought parameters and the solutions are related by a partial differential equation. And inverse problems involving partial differential equations are examples of nonlinear inverse problems. They are very common across all applications, so there's a need. So we need also to study regularization methods for nonlinear problems. So as usual, we generalize them up to operator equations of this form, where our F here, F for forward operator, is a mapping between Hilbert spaces X and Y. This time we have a nonlinear operator F, and F has a continuous operator. We also assume that F has a continuous Frechet derivative, which we denote by F prime. Now for the purpose of this lecture, we just consider a forward operator with a derivative. To relax that, that also can be done. There are results that already involve using a non-smooth forward operator. We'll not go there. We'll just consider this one. Okay, just to keep the course on an introductory level. So translating the Landweber method from linear problems to inverse problems is pretty straightforward. So as you can see in the formula over there, if you look at the formula for linear problems, and delta minus, let's say eta, then okay. So the point is that note this this is a gradient method for minimizing this. Okay. And then we know this is just the gradient. The gradient of in the steepest descent for minimizing this one. So The thing is that if we replace a times x by f of x, then we can simply translate this one to this one. And then I'll just change it into plus. So that's f. And of course, the gradient of, I forgot to mention. So if you have something like note the gradient for the steepest descent for this one will be just equal to f prime of x adjoint times f of x minus y delta. And that's why we have that iterative equation there for the nonlinear Landweber iteration for inverse problems. Now, it's not that its main difference there is, of course, f, and also by introducing the adjoint of the Frechet derivative of f, which is what you can see here. Okay. Now here we just use eta equals 1 for simplicity. Of course, you can introduce an adaptive step size here. It has been done. Okay, but for the purpose of this lecture, we just consider eta to be equal to 1. After all, we can do something to guarantee convergence of this one. But for this course, we'll just consider the part where we only deal with the convergence of the method. You can also derive the convergence estimate for this one. But first, a little bit about this method. And why is it more complicated to analyze than the Landweber iteration for linear problems? And still here, we'll consider a noisy data y delta. And we'll study its convergence via discrepancy principle, which is simply like this, just the same as the one we use for the linear method. And as you can see here, that should be tau. And here, the tau, which is the multiple for delta, is something that we have to choose appropriately. Now, I have to also mention that for nonlinear problems, the convergence will not be global. Unlike in Tikhonov regularization, that we take the minimizer x, the minimizer across the entire solution space. And that's because of how we formulated the method. As you can see here, at every iteration, this one changes, okay? Because every x sub n, you solve it to solve for f of x sub n. You also pass x sub n to the adjoint. So those are the computations that you need to do for the forward operator and for the Frechet derivative, okay? And because this term, this Frechet derivative changes in every iteration, unlike in the linear problems where it's just A star throughout. So the iterates for the nonlinear Landweber iteration will not remain within a certain invariant subspace related to a smoothness condition. Therefore, we need to impose some conditions on F. And these conditions are fundamental. Like for instance, you can assume that our problem is properly scaled. That means the norm of the Frechet derivative is bounded by 1. And for all x in this neighborhood around the initial guess x sub 0. And this is from the, actually from a reference, which I will mention later on. And this is what we mean when we say that for the nonlinear Landweber method, the convergence will not be global, which means you have to impose that the set of points under consideration is within a neighborhood of x sub 0. So they must remain close to x sub 0 from a certain within a certain neighborhood. Aside from that condition, we also need the following condition that is related to the nonlinearity of f, which is given by this inequality 4.3. And notice this left-hand side here is actually the error of the Taylor approximation of f. Roughly speaking, that nonlinearity condition tells us that f cannot be too nonlinear. That means it can still, approximated by a linear operator. In this case, that's the Frechet derivative at some point. Okay, so as you can see here, so that's the nonlinearity condition. It's a fundamental assumption that we use for analyzing the linear problems, and also a very helpful inequality, which can be derived using triangular inequality, is this inequality here. Okay, so for ease of computation, we use this one instead of this one, and note the conditions on x and x tilde. They must be within a neighborhood of the initial guess, x sub 0. Okay, and by taking note of these conditions, we have also this procedure in proving the convergence of this method. And not to prove local convergence, we will always assume that our linear problem has a solution in the neighborhood of x sub 0. And note that the local condition, just quickly mentioned here, the local condition implies the existence of a unique solution which is of minimal distance from x sub 0. And this time, we denote by x dagger the x sub 0 minimum norm solution. In other words, it's the solution of the nonlinear problem closest to x sub 0, which is the initial guess. Okay? And also for a proof of this result, I want to refer you to this wonderful reference by Barbara Kaltenbacher, Andres Neubauer, and Ottmar Scherzer, which is about iterative regularization methods for nonlinear ill-posed problems. It covers not just the Landweber method, but other iterative methods as well, such as the modified versions of it, and also some Newton-based methods, among others. Okay, so take note of that one. And also, the discussions on this part of the lecture will be based on this one. I will not put much of the proofs here. We will prove it here on the board. So here's a step. The procedure for proving the convergence is very much what we did for the nonlinear, or for the linear method. So the procedure will be very very similar. So here is how it works. So assuming the two conditions I mentioned hold, and suppose f of x equals y has a solution x star in that neighborhood of x0, if the Kate-Landweber estimate is within a neighborhood of the solution, then a sufficient condition for the next approximate xk plus 1 to be a better approximation of x star is that this residual should be bounded above by this multiple of delta. And note that eta there is really from the nonlinearity condition. Okay, it's not anymore the step size as we did in the linear problem. And also by this one, it's easy also to hold that to prove that the Landweber iterates all stay in the neighborhood of the initial guess, and that's important to guarantee local convergence. And we'll prove this one later. Maybe let's have a 7-minute break.